Okay, so just before I start, a quick reminder. So I just I posted yesterday the study guide for the exam. Um, the exam is Wednesday of next week, so like the last day before the spring break. So basically, my plan is I'm sure like I'll be done with the material by Wednesday. So next Monday, I definitely won't lecture anything. So I'll just turn it into kind of like extended office hours Monday. So I'll be here like answering just whatever questions you have. Um, the structure of the exam really it's like an exam about the simplex method. So like if you know how to do the simplex method, like you know what's going to be on the exam. Like there, I kind of like mentioned there, like that there are like four types of problems. One is kind of like solving the simplex method, kind of like from scratch. Then determining whether there is like the simplex method has like a finite solution or not, which we did like an example of that type last time. Then um, solving a degenerate system of equations using the simplex method, which I'll continue saying something about that today. And then the last topic would be that sometimes you do have to uh, find a basic feasible solution in order to start the simplex method. Uh, and that's kind of like the last topic that we'll discuss, which I haven't mentioned so far. But once I do that, that would be the last thing. So, in fact, probably if you have like, and I posted like some practice problems, but if you had just seen me like do the examples in class, it is tedious solve the simplex method. So I mean the problems won't be too long, but also I will just do four problems because I don't want you to kind of like rush with time. Like prefer you to have like safety amount of like safety net like for the time. So it would be one of these four types that I just mentioned. But the solution to each of the problems is the simplest method. It's just like slight like modifications of it. So everything is like the simplest method. And then if you made like if someone made a great request about the exam, I just haven't checked them, but I'll check them tomorrow. So if you can, if you still want, you can just do it through Gradescope, no rush. And if you took the makeup, I'll also grade it maybe tomorrow or Thursday, the latest. But yeah, I'll be done on Wednesday, and then next Monday would just be like come like off kind of like office hours during class kind of thing. So that you can have ask me anything that you want. But if you know how to do the problems that put on the PDF, literally that is like everything, and like like you just change the numbers, and that's like the problem of the exam because like it is just like learning how to do the skill. Yeah. Correct. Yeah. Four problems. Yeah. There are four types of problems, so one problem for each type. Yeah. No. One of the four like that would be too short. Yeah, like there are four problems. There's only one type of problem, which is the simplex method. It's there kind of like four mini variants. That's what I was trying to say. So really, if you know how to do the simplex method, like all the four problems are just that. It's just that there are variations of how to do it. Yeah. But in that problem, if when it's like a degenerate problem, I will say explicitly this is a degenerate problem, so that you know how to do. Like I will say ahead of time, this is degenerate, so like solve it the way that I'm actually about to solve. Yes. And like the one I mean I can put them here. Like it's kind of like it's on the study guide, but it's kind of like the auxiliary method, which I still haven't talked about. Then there's like the degenerate method, right? Which I will do today. Maybe today and next time. I think today, well, not tomorrow. Next time today, depending on how much time I spend on the degenerate method. Time today. Then whether like there's a finite solution or not, which we did like an example. Um, right. So this was last time. And then kind of like what I would just call like the classic simplex method, which is kind of like, there's nothing to do, there's nothing suspicious going on, like, like the simplex method, like, from scratch, like you just started, like, I'll give you like a system of inequalities, you turn it to the matrix, you add the slack variables, you solve it all like from zero to, from start to beginning, but there's nothing like of the weird stuff, like whether it's degenerate or things like that. And for this, like for the first two, I'll tell you, if this is degenerate, or I'll tell you, use like solve it, use the auxiliary method to solve it. So it is kind of like, there's not too much of like a decision on what type of problem you will get, because it will be clear from like the problem what I'm asking. But yeah, like that, those are kind of like the four variants which are really important about the simplex method to understand. And again, I even calling them variants, I feel like squishy, because like it is just really the same thing. It's like sometimes like they're like mini obstacles along the road, and then like those are kind of like the obstacles, like, so. Right, but they won't be too long. I mean, they're not, the problems themselves won't be that long, because like the simplex method can be like, time consuming. So okay, so oh sorry, yeah. The PDF problem we uploaded. I mean, so I did put the answers on beneath each problem, like the numerical answers that you're supposed to find. I probably will write like the steps for some selected ones, but like, I think the majority do have right now, like, you should find x1 equals 2, you should find x, like those like answer keys, they're already there. I will kind of write solutions for some of them, with all the steps, like how the reductions work, like so that you can see them. Um, but yeah, like at least like the answer keys, like, like you can find them already there. But because I did make this assignment ones for you to upload, if you have seen them already. Um, so I'll definitely write the solutions for the assignment ones. And then the other thing is like the difference between one type of the other is just like that the numbers are different, right? Like, once you know how to do one of each of the variants, the only thing that changes are really the numbers. So definitely I'll have like a solution written out for each of the variant, for each of these four from the problems. But for all the others, I did write what you're supposed to find, so that you can double check it. Okay, so like what I was trying to explain last time with this degenerate case, like just to go back quickly for like the previous, like the notes from last time. Um, okay. Again, what makes something like a degenerate situation is like in the case where, like, for example, there are only two variables, that like one of the points or one of the corners, if you like, um, is like the intersection of more lines that you would expect, because like in general, like a point, is the intersection of two lines. In this case, like the origin, like, it's like the intersection of the x and the y axis, but there's like a third line that's passing through the origin. So that's why the origin in this case would correspond to a degenerate solution. Which can also be determined in terms of this degeneracy of the basis that we talked about, like for the first exam. So like the two things coincide, but geometrically, that's what's happening. Now, the issue with that, with having degeneracy, sometimes it is an issue, sometimes it's not. Like, it's kind of like, it does depend on the specifics of the problem. But sometimes what can happen is that, and that's what I was trying to show you last time. So oh, I see here, like this is like from this step to the other. What can happen on occasions is that, like, say, when you do like the process in the simplex method, like the function that you're trying to optimize does not change its value. So like, um, here, like, like you kind of like do like this row operation, but the function remain at like value 0. And you would like the method to kind of always increase the value of the function, even if it's by a small amount, because that would guarantee that it terminates, right? If the function has like a finite, if the maximum is finite, and every step you're increasing the value, you're sure to terminate, because like there are only finitely many corners to consider. The problem when like when sometimes there's no improvement is that you can end up what they call like a cycle, meaning that the kind of like the algorithm just loops itself, and just kind of you keep going back and forth between previous corners without ever reaching the maximum one. So actually, I did write like on the PDF like a problem of those. Like if you want to try it out for yourself, so you would, if you solve it, like you get like into a cycle. It's just like those they're really big. So I cannot kind of like do one in class because it would take us forever. But I did write it on the PDF. Like if you want to kind of like work out the cycle, like see how it looks, and then you kind of like see that you enter like a loop and then you don't get out of it. But fortunately, there is a way to get rid of this, which is like this perturbation thing that I'm about to tell you. So in practice, one way to, and this is kind of like geometrically, you can see it here. The idea is that if you perturb the inequalities a little bit, you kind of like, by perturbing the inequalities a little bit, you kind of like move this line a bit. And so now it no longer passes through the origin. So it kind of like puts like the situation in the generic conditions. I'll kind of like explain that like with this example with this perturbation method. Yes.
Do you repeat why um I know that the origin intersects like the x equals y line and then the axes, but like how does that tell you it's degenerate?
Oh no, because it intersects three lines, right? It intersects the x-axis, the y-axis, and this line, right? The third line, right? So what it means to be degenerate, I mean, right, like of course you could check that from the from like the actual definition. I'm just trying to kind of give like an intuition, because that's kind of what I mentioned last time with probability theory. Like the idea is like, if you have two lines, right? The way to understand degenerate here, oh my God, what happened with my third pointer? Um, well, it's somewhere in there. But the way to understand degenerate is kind of like not generic. So like, when you have two lines in generically, like in general, they are not parallel, so they will intersect at a point, right? So again, kind of like if you had to make a bet, like with probability one, in fact, you can say with probability, with like almost like 100% certainty, two lines like intersect, but if in addition to those two lines, you had a third line that happens to pass through the exact same point of intersection, that is like a very unique situation, because in general, you would expect a third line to just kind of cross like the other two lines at two distinct points, if you know what I mean. So there is a sense in which like three lines passing through the same point is not generic, meaning like it doesn't happen like with frequent, like, with high probability. So that does like, what that means is that there are kind of more inequality, like more equalities that are kind of like if this is kind of like an inequality, right? It is like kind of like the origin is satisfying three, like at the origin, this becomes an equality, this becomes an equality, and this becomes an equality. So many inequalities are becoming equalities at the origin more than you would expect. So like you can see it in terms of in systems of inequalities, you see. Um, but geometrically, the idea is that, like, because the corners are always kind of like where the inequalities become equalities. Essentially, that's one way to think about them. But like for points on the plane, you would just need two of them, two of the three to become equalities. But at the origin, you have that x1 is 0, x2 is 0, and this one is also 0. So you have three instead of two. So it's kind of like, in fact, in terms of like inequalities become inequalities, if that makes sense. Um, but yeah, like, and then you do check, you can then verify that that kind of coincides with like the other definition that I had mentioned. But like the way to think about it more convenient is like they're kind of, yeah, that they're more equalities that are being satisfied at that point than you would have expected, if that makes sense. Um, uh, let's see. And it's not like the problem, and if you are calling it degenerate, it is something unusual. So it's not like a problem that really in practice is too problematic, because like the idea of this type of problem is it's very kind of like a special problem, like it's not, again, if you kind of like chose these numbers at random, this would not happen, like, like the numbers that you put here were like at random, like, or sufficiently general, like, so, and this is actually what I'll do. So just let me copy paste this like into like the next slide. So this was like the system from last time. And kind of like the idea is that you perturb the constant terms in the inequalities. Oops, so like meaning like you change the value of the constant of each constant by a small positive amount. So I'll call this because like the first one is like the first inequality. I'll call the first perturbation like the first change in the coefficient epsilon one. So if you like not that like this epsilon stuff from calculus is like emphasized too much these days, but usually when you talk about epsilon in calculus, you mean like something that is really, 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 really small. So that's how you should think about um those two numbers. So like here, epsilon one and epsilon two are really small numbers. So geometrically, at least in this case, I think um, what I like about this example is that you can kind of keep track of everything pretty straightforwardly. So what is like let's start with this line, right? So this line corresponded to x equals 2. So you're just shifting that line by a little bit of an amount, epsilon 2. So like it's just this line now passes at 2 plus epsilon 2 instead of 2. But and which is not like a big thing, but the first inequality that's kind of more important because if you look at this line, like let me write it. I'll write it in the usual XY notation instead of like X1, X2. If you have X1 minus X plus Y equals epsilon 1, that gives you that Y equals X plus epsilon 1, right? So by having added this perturbation term, now this sign does not pass through the origin. So you have moved it away from the origin. Oh, okay. And so in the perturbed system, the region which was originally a triangle becomes kind of like this quadrilateral type thing. So the way to think about it is kind of like almost like an animation where like, this is the point 0 epsilon 1, and this is the point, you know, 0 epsilon 2. Oh, sorry, 2, 2 plus. At that point also doesn't really matter. Like the only one that matters is like the blue one because that's like where the issue was occurring. But the idea of like the imagine that you started lowering, like shrinking, like taking a limit of as epsilon one goes to 0, like making it smaller, smaller, more smaller. Then this line goes down, 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 down until it crosses like the origin. So essentially, what happens is that the triangle is kind of like the merging of two of the corners, right? Like or in the perturbed system, there are four corners and two merge at when epsilon one was 0. So that's why it was degenerate because it's really kind of two corners at like in the same spot in some way. That's one way to think about it. Um, that making sense, kind of what's going on here. Of course, in this particular case, you only had to perturb that equation, but you have to think about it kind of like from a general perspective. In a general perspective, you don't know how the figure looks like, so you wouldn't know which ones to perturb. So that's why you just perturb them all, right? So let me just make that remark. In this particular example, for this example, perturbing the first inequality would have been enough. But you have to pretend we don't know how to draw anything, right? Like, so if you don't know how to draw anything, you don't know what to perturb, so you perturb everything. That's kind of like the idea. You have to be more kind of like democratic. Like everyone gets like the same treatment, like you cannot take favorites. Like once you have like the picture, of course you cheat and you know what would happen, but perturbing the first inequality would have been enough. Oops, sorry. I always forget to scroll down. Okay. But like you have to, but but in general, you wouldn't have access to the like how to the picture, But in general, you perturb everything to be certain. Since you don't know how the picture looks like. Is that okay? Is that making sense? And in practice, kind of like as a convenience, which is not super necessary, but like, and it wouldn't make much of a difference because our systems are relatively small. But as a convenience, like here you have to keep track of two parameters, which is how they would be referred to as epsilon1 and epsilon2. If you had like imagine like 100 equations or 100 inequalities, there would be epsilon1, epsilon2, epsilon3 up to epsilon 100. So that's a lot of parameters to keep track of. So as a convenient way to perturb them is to think of like all of these parameters as kind of like just the power of some other number. So like epsilon1 is epsilon and epsilon2 is epsilon squared. Like, so you write them all like as powers of a single number, as different powers of a single number. So in practice, to reduce the number of perturbation parameters, uh, you write them as powers of a single number. So by that, I just mean that you take epsilon1 to be epsilon, epsilon2 to be epsilon squared, epsilon3, if there were, like there's none here, epsilon cubed, epsilon4 to be epsilon to the fourth, etc. Okay. Yes.
There is like your powers instead of like multiple again.
Oh, right. That's a good. I did was we're going to make mention like something like that. For example, let's just ask something answer something like which is a little bit more simple than what you're saying. Why wouldn't I just take them all to be the same, right? If I take them all to be just epsilon, I do run the risk that because we're going to reduce with row operations, right? So row operations are like multiplying rows by constant coefficients, right? So I do run, if I call all the parameters just epsilon, I do run the risk of like, putting myself in the degenerate situation again, because like having all the perturbations be exactly the same is like a very special condition, if you know what I mean. Now, why wouldn't I use like, for example, epsilon, 2 epsilon, 3 epsilon, right? Like, which is kind of like just like a linear rescaling, because it's kind of like similar, because if you think about like doing the row operations, like they will, like the row operations are always like rescalings of the rows, like, so it does increase the chance of like, of like accident, like, creating degeneracies along the road. And the power has the advantage that kind of, like, I don't know if like words like the engineering course, like, or the math course where this will be discussed, but kind of like these you have to imagine that epsilon is going to zero, right? But by using powers, these parameters go to zero at different speeds, right? So what goes faster to zero? Like epsilon to the 4 goes faster to zero than epsilon squared, for example, right? Oh yeah, like we can do like, it's kind of like just you kind of like see it from the graphs of like y equals x, y equals x squared, y equals x cubed, like the higher the power, the rate, the approach towards zero is faster. So by having like different powers, kind of like they're converging to zero at different speeds, and that kind of like also like puts it kind of like in the generic situation, because then that kind of like it's kind of like a race like towards the origin. And so this one is moving way slower than this one, than this one, than this one. So like they don't have like a chance to intersecting, which is what you want to prevent, like in the degeneration case. No, so it's not that powers have to be necessary, but you do want something that kind of like doesn't put you at risk of like, by some linear combination of the rows that you bring it down to being degenerate. And this is kind of one of the easier fixes. Is that making sense kind of?
Yeah.
Um, right. So it's kind of like similar to, this big O notation or little O notation. If someone has ever seen that, like in discrete math, I don't know, like similar to why like an exponential grows faster than any polynomial function at infinity, or like any polynomial function grows faster than a logarithm at infinity, like x, like these different powers just converge, go to zero at different rates. And so that kind of like is good to have around. Um, but at least definitely from an algebraic point of view, it does make your life easier, because then now you just have to worry about a single parameter instead of like many different ones. Um, so in this case, we just like using epsilon and epsilon square with this idea, like by the way, I think have you ever yet received like the mid-course semester evaluations, or you still haven't received the link? I think at some point very soon you have to give like the evaluations for like how the semester is going. Probably they post them before the spring break. But yeah, like, I will send you a reminder, but it would be useful to have like some feedback in terms of like, because like after we return from spring break, we actually are moving more like into like the more interesting part of the course, I would say, which is what we know the simplex method, and we can use it for cool things. So like yeah, like I'll remind you to give me some feedback, because that way I can kind of calibrate like the rest of like the classes that we have left after like the break. So uh, well, let me put this up. I actually had it here. Let me copy this here. So this is epsilon squared, which if you want to write into Slack using Slack variables, right, to get like equalities. So how many Slack variables do we need? We need two, because we have two inequalities. So minus x1 plus x2 plus x3 equals epsilon, and then x1 plus x4 equals 2 plus epsilon squared. Okay, so that is how the equality equations look like. And again, as usual, um, you read off the coefficients of like the interesting equations into the matrix. So like the last two gives you -1, 1, 1, then epsilon, and then 1. Oh, sorry, I'm going to have like, I need a column for the last one. Yeah. 2 plus epsilon squared. But what I was, and again, but if you want to use the simplex method, what I have said is that it is convenient to have like this last row and add an extra row where you just keep track of like the function that you're maximizing, right? So this is like the original AX equals B, but now we add the row, we can add an extra row and column. Right, because if you I will always call like the function we're maximizing z. So in this case, z equals just equals x2, so which you can write as minus x2 plus z equals 0. So you think of like an extra column for the variable z, and another row for that equation. So it's kind of like adding an equation to the original matrix, which I mentioned. You can. I'll usually we'll put like another like horizontal line or something to kind of like separate it. So again, not that you have to, but just to like indicate what the columns represent. Like those are the columns for the original variables. This is a column for the z variable, and this is like the column for b. At a minimum, if you know, I do like the fact that this, like, what is nice to setting it up this way is that you are keeping track of like the function, you know. So once you're done, you can just read off that entry, and that would be the max value. Um, but like, do put like a line or something to separate them because otherwise you could get confused um when solving the system. Oh yes, yeah.
So I know you're saying like adding the last row is optional,
Hmm.
but that's like important for like the strategy you taught us.
Right, no, like if you want to do it, yeah, yeah, yeah. No, like I guess what I would call like I mean, really the most this column is really optional because this is completely optional because this will always remain 0, 0, 1 throughout the entire problem. Because when you do row operations, since these are zeros, you know, they won't ever change. So this column I would call completely optional. But it's just like, useful to have it that way because um but yeah, like, you know, they're you know, like no, like definitely for like the matrix version of like the method, you do need to have these coefficients. Um, but not, at least not the column. That would I would call like optional. Um, there's another way to solve this. The if you have been reading the book solves like the math, like the problem without ever switching to matrices. So you just always write it as systems of equations. I didn't go for that route because I do prefer like the matrix version, and I feel like that's closer to how you would think about it just coming from linear algebra, right? So that's the only reason why I'm kind of using the word optional because, like, you know, there are ways to just avoid like the matrix version completely. But yeah, if you stick with the matrix version, then yeah, you do need like to keep track of this last row. But yeah, like the column for C, I guess like that's a little bit more like not necessary because it will never change. It will always remain like bunch of zeros and one at the end. Like so. Okay, good. But I do find the matrix method like very elegant, and I kind of like it once you get used to it. And something that, again, if I have time, I will mention it once we talk about the last topic for the exam. But notice like because of like how most of our examples have a reason, you know, you always when you add slack variables, you always get like these copies of the identity matrix. And secretly that has been useful up to now because like again, when you start the simplex method, you really have to start it at a basic solution, right? Um, it's just like in this case when you have like the identity matrix like inside the matrix, like the basic solution is just oops, like the basic solution is just like the one that corresponds to like the identity. So that's why I haven't brought it up too explicitly, but once we finish this topic and we talk about the last one, I will kind of like bring this up more like clearly, so because it's kind of like the only thing where there's like something to kind of like also keep an eye on. So okay, so that is like the presentation. And then according to the simplex method, you look for the largest negative coefficient in the last row. There's only one choice here, so we're good. So I focus on that column. Let me copy paste this here. Okay. And now I do look for the ratios, right? And so I do the ratios. The ratios are so epsilon over 1, which is epsilon, and 2 plus epsilon squared over 0, which again, you can call an infinity or you don't do it if you want, if like the ratio is 0. Um, so you choose like the smallest positive ratio, and then now this one is like that ratio is epsilon. So the choice, So we focus um of this entry, and the idea then, sorry, I should let me give you some time if you're copying, because I'm cheating by just using copy paste on the tablet. That's just one of the nice things why of writing on the tablet with for this course, because otherwise it would take forever to write all these steps. Um, and then the idea, again, is that you turn this one, like this is already a one. If it had been a two, you make it a one first. Like you always want to turn it into a one if it wasn't a one already, and then you make zeros everywhere else. So it has to become like a column of one, like zeros, except for like an entry with just one. So there's like this is already zero, but I do have to make this one into a zero. So I'll do that as what do? I do row one plus row three, and that should be enough. Into row three. And let's copy this. So negative 0, 0, epsilon. Let me copy it to just give you some time to catch up, because otherwise, um, 2 plus epsilon squared. And let's separate this one. So when you add, you get negative 1, 0, 1, 0, 1, epsilon. So far, so good. Is that making sense? Questions up to now? And you see here, the difference with before, like if you remember when I showed you the earlier slide, is that now the function did switch from zero to epsilon. So it did grow in this step. Before, if you had tried to do it without perturbing, you are stuck. So it was at zero and going to zero. So there's no progress being made if you think about it, like at every step wanting to increase the value of the function. So now it did increase by an epsilon amount, which again, when you think of epsilon as being super small, that wouldn't be a big increase, but like, it's better to have like some increase than no increase. So now increased, which is good. But still, we're not done, right? Because again, we stop until every entry here is positive. So we still have this negative one that we can focus on. Oops, let me. So again, like because of the negative one, I'll choose that column. And so what are the ratios here? The ratios are epsilon divided by negative one, which is negative epsilon, and 2 plus epsilon squared divided by 1, which is just 2 plus epsilon squared. You have to choose this like smallest positive ratio, and like there's only a positive ratio. So you have to choose like this one. So like, let me. So this is like the one that was selected. Oops. Okay. And again, the rule is that everything that is not this entry on that column has to be turned into a zero. And if this entry had not been one, it also is made into one. So if it had been seven, you have to do 1/7 row two first to turn it into one, and then you use that one to make zeros everywhere else. It's kind of like, kind of like this pivot stuff, like when you were reducing the matrices in linear algebra, you would first make the first non-zero entry would turn it into a one, is similar to that. But now the thing is like this is kind of like scatter, because we're not row reducing, but it's kind of like, but we're still doing row operations. So to make zeros, you do row two plus row one into row one, And I will also do row 2 plus row 3 into row 3. And that may be the last thing that we need to do. Let's see. So when you add the two rows, the first one becomes 0, 1, 1, 1, 0. Then 2 plus epsilon squared. And then the second row was left intact, right? And then you add when you add the last two, like the second to the third, you get 0, 0, 1, 1, 1, and then you add those two together, you get 2 plus epsilon squared. Okay. Is that okay? Does that make sense? And now you terminate it because every entry in the last row is positive. So that terminates the algorithm. So terminates. And again, let's just do it for a moment because it's kind of like illuminating to read it off back as a system of equations, you know, because that also makes it more transparent why the problem algorithm terminated. So again, like the idea, oops, sorry. The idea is that Z represents what you wanted to increase the most, right? Like that's the name that we're giving to like the function that we're maximizing. So you want this to be as large as possible, right? Because now all the coefficients are positive, to make this as large as possible, you just shrink each of these to 0. Because again, all the variables are non-negative in the simplex method. So for Z to be the maximum it could be, you just like force x3 and x4 to be 0 in this case. If they were still negative, that argument wouldn't work, right? Like it's like a more complicated thing. But like to make this like the largest, you just decrease this the most you can. And that is fine because like the coefficients are positive. So that forces x3 and x4 to be 0. And those are like the non-basic variables in this case. For this, so there was secretly a basis, those were like the non-basic variables. And once you know that those two variables are set equal to 0, that is super easy to find the value for the other two variables. So the basic solution is x equals 2 plus epsilon squared, 2 plus epsilon squared. And then 0, 0. That makes sense. And the max is the value for z, right? So the max is z equals 2 plus epsilon squared. Well, if you want to go first.
Yeah, just like when you check that the last row is all positive, it would never be the last two columns that aren't.
No, it doesn't necessarily need to be the last two columns, correct? Like sometimes it could have been like, they could have been different columns. Like it's not like right. So right, in this case, it happened to be the case that like the positive entries were like the last two columns, but it could have been like, if I had maximized a different quantity.
Oh, yeah, like, I guess what I'm saying is like, when you're checking that they're all positive, like, it would never be the, uh, Z or the B column that would have.
Oh, right. Yeah, you focus on like, right, like, sorry, I now understand you. The positivity is checked here, yes, like the ones before Z. The Z one, like, if you want, you can add it because it always remains one, so it's not a problem, you can say, that's fine, but yeah, like it's only until
But
Z.
you wouldn't have a case where it's like all columns are positive except for like your B value columns.
I mean, I suppose like no, you could like, I mean, the B value could be okay, that sometimes happens like no, the B value is fine. The optimization can like the max could be negative. Like the max can be negative, right? That's not an issue. It's just like for example, this is super silly, but um just to answer your question, like let's go. You were trying to, if you look at the picture, right? What was the problem? We were trying to find the maximum of x2, right? X2 is like the y coordinate. So you're trying to find the maximum of the y coordinate. In this picture, first, it's kind of clear that this is where it should happen, right? And then if you kind of go through the entries, you see that those are like the coordinates for that point, right? 2 plus epsilon square, like, those are, but like imagine, imagine like very simple change. I had multiplied x2 by -1. If I had just put max of minus x2, then the z value will be negative. You know what I mean? So like no, like the positive, and in fact that sometimes happens when like I don't know if you remember, I had mentioned like a few classes ago that a minimization problem is a maximization problem secretly because the mean of a function is the max of, like where the mean occurs is where the max of minus the function occurs. So, sometimes like you kind of get like, you can switch a mean into a max just by multiplying by -1. So like it is natural for like the max to also be negative. That's totally fine. But yes, like and so in general, like definitely what you were saying is correct. Like when you look for the positivity requirement, it's only until column Z. And column Z, again, if you want, you can add, but definitely nothing with column B. What were you going to ask me?
Yeah, how do we know that X3 and X4 are zero?
Oh, it's kind of like what I was saying because you have to imagine I want to increase Z, right? Like that's what I'm trying to increase as much as possible. Uh, These all are non-negative numbers adding to something. So how can I make the third one the largest? You force the other two to be zero. That works because they're all non-negative, right? If it can be minus x3 plus x4, that is where it gets messed up. And that's why you have to, in that case, you would continue the simplex method, right? Because that's why it requires all the variables to be non-negative so that it like kind of holds. Yes.
So for the, well, so the like the dirty equation, okay?
Mhm.
There are like other variables. Like there's still a positive, like there's still a positive number of like, non-basic variables, so like that balance there.
Sorry, what are you saying? Like repeat.
Right. But there's only x3 plus x4 plus z equals 2 plus e plus f squared, right? So
Right.
what if there's like, for example, x2 plus 15 plus x4 plus z equals 2 plus z.
Oh, right. Like it doesn't matter like how many variables are here, as long as they were all being added positively, with positive coefficients. To maximize Z, you would require like all of the others individually to become zero, right? Yeah. So like the number, right? Like good point. Like the number of variables here, like doesn't really play a role. What really plays a role is like the fact that there were positive end coefficients. The other thing that I was going to say is that the cool thing is that if you take epsilon going to zero, then you get the maximum to the original solution. So what is like the limit? Now take epsilon. I mean, you can think about it more cleverly. Oh, it's kind of like a limit thing where epsilon is going to zero. And then the max to the original problem is 2, 2, 0, 0. And the max is 2, which kind of like, if you remember like the original triangle, it is fine because like the triangle, the hypotenuse was y equals x. So like, like now the x and the y coordinates are the same. So like, so in fact, like, what's nice about doing it this way is that it also is a way to solve what you call like a parameter family of inequalities, because literally without noticing, you solve infinitely many simplex methods at once, one for each value of epsilon. So like sometimes there are these like that's what it called, like sometimes in the literature, parameterized simplex or parameterized systems, because like there's like a parameter in the inequalities, which makes sense because like sometimes imagine that the cost is not known, like so maybe you don't know like the cost with precise certainty, or you want like there are fluctuations in the prices from day to day in the stock markets, right? So you don't want to. It would be silly to solve the simplex method just for a specific value for the avocados, right? Like maybe it's $2 plus 1 cent or $2 minus 2 cents. Like there could be some variation, and sometimes like the variability is very easy to introduce just like by putting like the epsilon stuff. So it's like it's not even for degeneracy. It's kind of like philosophically important just for other stuff where it's like, okay, sometimes like you don't really know the exact number for like the cost or like the selling point, or like those fluctuate. So if you have like but it's like the fluctuations are not too big, then you can kind of like solve like all that family in like at once, in a sense. Yes.
But yeah, like the only important thing of this thing, independent, right? That maybe not maybe.
Right. Yes. Like they do have to be non-negative and right, independent. Yeah. Well, there's like actually like a trick. I mean, yes, like even like I mean, like there's like a which we didn't go to because like most of like for most problems like they're already set up so that the variables are not negative. But if you have a variable which could be positive or negative, you can write it as a difference of two positive variables, and then you kind of like add like an extra variable. So like there's like you can always rewrite it that way. I think the book does mention that at some point, like at the beginning of chapter 1, if you read it. Um, but yeah, like so the non-negativity is always something you can kind of like get more or less for free um here. Okay, perfect. No, but I think I do find this like very elegant, so that's why I wanted to discuss it with more details. But again, like yeah, when there will be like a problem like this, like with the degenerate on the example, I'll tell you it's degenerate, so that you have to perturb, and you do like the system, like get it done. Is that making sense? Okay, now the last topic that I'll just start for today, because I don't think I'll get to finish it, is like this auxiliary simplex method, or like not auxiliary simplex, but like as auxiliary system as for the simplex method. So auxiliary optimization problem. Okay, let me go up. Let me find the example that I wanted to. Okay, so let me illustrate this with a point. Let's see. Okay. Again, let's start with like a picture on the plane because it's easier to understand. Um, um, Let's say x1 plus x2, x1 greater or equal to 0, x2 greater or equal to 0. And then I'll put give me I think I'll have to change some of these coefficients. Let me see if like why should I put them? Okay, let's see if that works fine. Okay, yeah, I think this should be fine. I'll draw it and we'll see if I have to change it or not. But I don't know if you noticed that what's a little bit different with how I have thus far is that this one is fine. This is a less or equal version, but this one is greater or equal version, right? Which can be turned into a less or equal, and I'll do it in a moment. But you know, when you're plotting this for the first, like it is sometimes to have like the variables with positive coefficients, but better. So what does this look like? Again, let's take first like the first equation, which is x plus 2y equals 2. So that's 2y equals 2 minus x. So y is 1 minus x over 2, right? So it's going to be L1. Okay, yeah. Oh, yeah, it's fine. Cute. Let's actually make this a 4 to, sorry, like just to make this nicer. Yes, so that they don't intersect like that is. Okay, so that is 0, 2, and then this will be 4, 0, right? Okay, and then the other one, oh, right, like the intersection happens like later on. So then the other one, let's say, is they like I'm going to try to make them so that they don't look parallel. It's like they don't intersect on the first quadrant. So like the other one is y equals 1 minus x. Okay. So let's see. You need, yes, like this would be. Yeah, it's fine. Like the intersection is outside the first quadrant. So like this is like the region here because but okay, so that's kind of roughly what the region, like the convex region corresponds to in this case. And of course, like you know, when it's like graphical, you can just like uh, find the max and whatever. Like, but I'm going to show you something that you know, is a bit not super clear with what we have done before. So sorry, like I've mixed these two. At least I'll explain to you what the problem is today, and then like next time I'll solve it so that you see what the issue is. Okay, so the biggest issue, caution, right? Like this is greater or equal to, so you have to be careful there. So we have to rewrite it as less or equal, right? So, you know, like that's not too bad to do. You just multiply by -1 both sides, and that just like fixes like minus x minus y less or equal to -1. Okay. And then once you have it all like in this inequality version, like with the less or equal to, you can add the slack variables, right? So this gives you max, oh, so, like, and I wrote x1 plus x2 upstairs, like, so it was like, so it's x1 plus 2x2 plus x3 equals 4. And then minus x1 plus x2 plus, sorry, minus x2 plus x4 equals -1. Is that okay? Oops, sorry about that. How are we doing so far? So good. Questions, something? Yeah.
The original equation less than two.
Oh, what did I do? Oh my God.
Oh, no.
No, I did fix it. Sorry, like I had changed it because I did want them. Otherwise, I mean, not that it was super necessary, but if I had kept it at 2, then these 2 points. So it's more like, I mean, like one and more corner, I guess, like, fewer, like just to have more corners and like not another triangle, because everything has been like a triangle so many times. So, okay, actually, so what okay, this is like a good segue. Okay. So if you write this into matrix format, right? This is 1, and I'll just do first, like before, like putting the optimization function, right? 1, 2, 1, 4, and then -1, -1. Sorry, I forgot the 1, 0 for like. Okay. Uh, so everyone with me? Okay, here's like, okay, there are two different things that you can notice in this example. There are equivalent ways of thinking about it. One is like this in the natural presentation. Now we do have like a constant term, a coefficient term here that is not positive, right? Like this is the kind of like, I think the first example where like naturally like it didn't come out like every single entry of B positive, right? Okay, so let me write that down. At least I'll mention like yeah, I'll finish soon, but like so this is not positive. Why is that like a useful thing to notice? Because if you were saying, and again, this is something that I kind of like swept under the rug until now because it had not happened before. But the idea of like the simplex method is that you initialize the algorithm at a corner and then you find like the adjacent corners where you start increasing the value of the function. But the idea is to start at a corner that is feasible, right? Like that is like that satisfies all the equalities and the inequalities. So if to find like a basic feasible solution, right? Since this is like a 2 by, like, since this has 2 rows and 4 columns, we needed like a 2 by 2 invertible matrix. The most obvious one, and that has been the case in all the problems we have done, is like that you have like this always like mini block of the identity thanks to the slack variables. So like you would have used like the basic, like the columns 3 and 4 in this case, right? But now, because of those would have been the basic variables. And now the values for those basic variables, right, would have been x3 equals 4, but now it's x1 equals -1, right? Because like that's the point of using the identity, that there's not much to think, it's just like the coefficient, like the constants, like the basic solution would have been like what 0, 0, 4, -1. That's why in the first exam I asked you, find a basis, is that basic solution feasible or not? Because now this is like an example where the obvious option, right? The obvious option, just because it was like the identity, right? would not have been feasible. It's a basic solution, but it's not feasible because like one of the coefficients is negative. Is that making sense? So let me emphasize this. So this is basic solution, but not feasible because of this coefficient. Okay. Is that making sense so far so good? And then okay. And then you could say, well, that's a bummer, but then just like find another basis. That shouldn't be too hard. Of course, this is not too hard in this case because this is like 2x4. Like, like, yeah, just like, I'm sure like if you grab another like of this 2x2 invertible matrix, probably like you would find um one that's feasible. But that's not the philosophy that you have to keep for these problems. Like the philosophy that you have to keep for these problems is like, oh, what if you had like a 10,000 times 11,000 matrix? And you would have like this friendly matrix identity coming from like these slack variables, but now we're stuck because this stupid negative coefficient is ruining everything. And you don't want to navigate the other columns, which are not like the already ones, like the ones from the identity, because if you start doing that, you're just going through the corners. And then you might as well forget about the simplex method, right? If you just start like going through like all the bases, that's not the point of the simplex method. So what I'm trying to say is that here, like the idea, and this is like what I meant by auxiliary system, the idea of this auxiliary system is that we will set up a system to solve that will produce for us like a basic feasible solution to start the algorithm with, instead of like just going through like the trial and error like the other corners. So, whoops, what happened? Oh, like static electricity turned this off. What's going on here? Sorry about that. I'm almost done. Like I'll just finish here because it's kind of like good to start with this like fresh, like next time. But the idea, right? Okay. So the idea is that you don't um, want to find by trial and error uh, basic feasible solution. Instead, we will solve an auxiliary problem that will produce a feasible solution for us, and that's what I'll mention next time. Instead, we will solve first an auxiliary problem which gives a basic feasible solution. And once you have that, then you can run the algorithm as before. Once you have like, because again, and I'll kind of like do all of that on Wednesday. I'll kind of show you how that works. But like that's a subtle point that we didn't really care up to now, because up to now you had always this identity matrix and every coefficient was on the last column like of constants, like non-negative, so nothing to worry about. So you kind of like don't even think about it. But this happens basically every time one of like naturally you have like this greater or equal to like inequalities, like usually that's when instead of like a less or equal to, when you do the flip you get these negative signs that messes everything up. Okay, so let's finish here and then next time I'll tell you about that, and that will be the last topic for the exam. And yeah, on Monday, as I was saying, like I'll just answer whatever questions you have about like so there I won't lecture anything.
More questions. So I guess the first one is just like, could you explain like what step 2 is? Because I